All right, second lesson of the day. This one should be pretty short, I believe. So go ahead and copy down everything you see. Pause me. All right, let's review what we know about the graph of f of x equals 1 over x squared. It's similar to the graph of 1 over x, except instead of in quadrants 1 and 3, it's in quadrants 1 and 4, because all the y values are positive. No matter what I plug in, I'm going to get a positive out of this. So if I plug in a 1, I get out a 1, and if I plug in a negative 1, I get out a 1. Okay, and then we can plug in small values for x, like 1/2 and 1/10. The y values are going to get really large, right? If I have small values in the bottom, then the y values get really large. And if I plug in large values in the bottom, then the y values get really small. And then the same thing happens over here. And we have asymptotes, just like the 1 over x graph, on the x and y axes. So a few things I want you to memorize for this graph, because you're going to be doing translations and things like that on this. There's 2 asymptotes on the axes. I want you to memorize that. The points, 1, 1 and negative 1, 1, and the general shape. And then you should be able to graph, for example, like f of x equals 1 over x minus 1 squared. That's just shifting everything to the right, okay? All right, in general about asymptotes, you can pause me again if you want to copy all of this down again, or I mean the rest of it down. All right, vertical asymptotes occur when the function is undefined. So you can see this function is undefined at x equals 0, and there is a vertical asymptote at x equals 0, okay? Asterisk, important. Functions cannot cross vertical asymptotes. Functions cannot cross vertical asymptotes, ever. Horizontal asymptotes are just about the end behavior. So as x goes to infinity, y is getting really close to 0. As x goes to negative infinity, y is getting really close to 0. We talk a lot more about horizontal asymptotes in calculus, and these definitions kind of drive me bonkers when I teach calculus because people try to rely on them. We actually explain these definitions in calculus. We can't do it before then, though, okay? Horizontal asymptotes can cross, I should say functions, sorry. Functions can cross horizontal asymptotes because they just describe end behavior, like I just mentioned. So we might see graphs that cross the horizontal asymptote in the middle, but then the end behavior is what we care about. Excuse me, way off to the left and way off to the right. All right, so if the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is y equals 0 every time. If the degree of the numerator is equal to the degree of the denominator, we do lead coefficient divided by lead coefficient, and you'll see we're going to do that right down here. So if you don't know what that means, don't worry. And then oblique asymptotes, I guess I need a parenthesis here. We're skipping those. But the third option is if the degree is greater in the numerator. And we're not talking about oblique. So I was pretty careful in assigning problems and making sure that I did not include oblique asymptotes. But if you find something where I missed it or whatever, I'm not holding you accountable for oblique asymptotes at all, okay? You do not need to know about oblique asymptotes. It won't be on a quiz or a test. You don't need to do it for the homework. All right, so find all the asymptotes. So first thing, let's just start with vertical at the top. Vertical asymptotes occur when the function is undefined. So I need to figure out what the factors are of the bottom. A function is undefined when the denominator is equal to 0. So there are vertical asymptotes at x equals 4 and x equals negative 3. Okay, this is Algebra 2 review still. Then for the horizontal asymptotes, I need to analyze the degree. The degree of the denominator, the degree of the numerator is equal to the degree of the denominator. So I'm using this. I'm going to take the lead coefficient on top divided by the lead coefficient on bottom. So I'm going to write y equals, remember that asymptotes are lines. They're vertical and horizontal lines, so they need to have x equals and y equals in front of them, okay? I can't emphasize that enough. Lead coefficient on top is 2. Lead coefficient on bottom is 1. So the equation of the horizontal asymptote is y equals 2. Easy peasy lemon squeezy. I'm so glad we're skipping oblique asymptotes. We pretty much, they don't really come up after this. So, all right, last thing, removable discontinuity. A removable discontinuity happens when a function is factorable and the factor would cancel out. So you might notice that I really like this quadratic. I use it often. So this function simplifies to this. So if I were to graph f of x, the graph of this function is going to look just like the graph of this function with one exception, and I'll explain in a minute. So I'm going to graph this. I'm going to start at 3. The y-intercept is 3, and the slope is 1. And I'm going to keep going with the slope. I wish I did this on graph paper. I'm going to be careful and keep going with the slope. This function is undefined. Let me do this in green. This function is undefined when x equals 4. So if I keep counting out my slope, I'm at x equals 2 right now, so I'm going to go x equals 3. My next point would be at x equals 4. Let me make sure that lines up pretty well. Yeah, I think it does. Okay, when I get to x equals 4, I need to show that it's undefined. There's not an asymptote there. The way that I know there's not an asymptote, when a factor is removed, you might want to write this down. Okay, pause me as I say it so you can write it down. When a factor is removed, there is a removable discontinuity. That is a hole. I'll say it again. When a factor is removed, there is a removable discontinuity, which shows up as a hole on the graph. So I'm going to count out the slope one more time. And it looks exactly like the line y equals x plus 3, except for that hole. Okay, that's called a removable discontinuity.